Thanks for the introduction, and thanks the organizers for this fantastic workshop. I've been coming here 2 years in a row, or at least to this idea of 2 years. It's nice to be back, also in this interesting institute. So, some people have been obsessed with classifying topological phases, like our chairman here. I am obsessed with quantization and finding quantized responses in topological matter, because if you think about it, there are experimentally not so many quantized observables that we have observed as a community. So yeah, of course we know about the quantum Hall conductivity, the quantization in linear response of the transverse conductivity, which is a stereotypical example of quantization of topological states. I like actually an experiment that one of our organizers did, which was showing that even in a 3D measurement you could get quantization, which is you take a TI, you gap it with a magnetic field, and you shine light and you look for rotations in the plane of polarization. And by measuring Karen parity of rotation, you can kind of smartly kill all the non-universal parameters and measure something quantized. So that's, I think, a very neat experiment. But recently, also with some people in the audience, like Fernando and Yang and Minghai have also been studying this kind of things, also Inti. We kind of pushed the barrier to nonlinear effects as well. And what, in particular, we were interested in what types of effects could be quantized in nonlinear optics, so going to the next order. And also in metals, rather than insulators, which is the typical place where we find quantization. So this you will hear about in Fernando's talk tomorrow. So this is one of my motivations, like trying to find quantization in experiments, or help to think of experiments that can show quantization kind of simply. And also, some kind of side question is, how does quantization really look in real space? Sometimes we don't think about this, but in fact, you can, following some more or less recent works, you can also map somehow where is the quantization in real space. So I'll get to that in a second. So, my setup is always going to be shine light, absorb, and look for some response, some optical response. And my punchline is already here. Circular dichroism is gonna make you be able to distinguish different types of chiral higher order topological phases, and it's gonna be actually quantized to integers. So I'll explain briefly what 3 higher order TIs are, although there have been introduced, like the helical version of the models I've been using have been already discussed. And I'll also explain what I mean by circular dichroism. So the first thing that you might not know, but it's a very old result, is that actually circular dichroism measures DC Hall conductivity. And so I'm gonna be brave here and guide you through a very simple derivation of how this is true. So take the absorbed power. So if you look into an ENM book, you'll see that it's just the real part of this product of J times E, J star times E. So J is the current, E is the electric field, P is the power absorbed, A is the area of your system. Now, go assume linear response and introduce this here. It's trivially this. Now, if you think of circularly polarized light, your electric field looks something like this. It has this funny plus minus I into I omega t. Now introduce this, really very simple. And you get the real part of the longitudinal conductivity plus minus the Hall conductivity, right? So now you already see that you can kind of, by subtracting left and right polarizations, you can already isolate the sigma xy, which is what I'm going to do. Now I'm going to use the property of the English language, which is that power absorbed is the same as absorbed power, so the commutativity of the English language. And now I'm going to say that power absorbed is also the energy that you absorb, times the number of carriers that are being excited due to that energy. So that's h bar omega times the excitation rate, gamma. And this depends on the polarization in general. Now, right, so now I'm going to do what I was promising, just subtract left and right and integrate over frequencies. Okay? So this is what this delta gamma that I'm going to plot many times in this talk is going to be. So just left minus right absorption rates integrated over omega. Now, if you do this just by the formula that's up there, you'll find that you exactly isolate sigma xy, the imaginary part of sigma xy, over omega. And now you know that for analytic functions, basically the real and imaginary parts are related by Kramer-Ströning. So this immediately gives you the real part of the Hall conductivity. So just by measuring absorption, you can measure the DC Hall conductivity provided you integrate over all frequencies. Okay, so this is kind of already well known. It was known by Bennett and Stern. Stern is not the Stern we all know. And also Souza and Vanderbilt kind of pointed out in the model language. Now, if you have a 2D insulator, this immediately implies that this is quantized to the Chern number of the field band or some of the field bands. Okay, and in fact, you can even do this experiment, and has been done in cold atoms by this cold atomic realizations of Chern insulators. They have driven some collection of cold atoms into a Chern insulator state, and then further driven the system with circularly polarized light, which means just shaking in their case, and measure this quantization. Now the thing is that if you actually do this driving to a whole system, whole finite system, you would actually get 0. So actually the total circular diagram is 0 in finite samples. So let me prove this to you in two different ways. One is actually related, so you can see this either in real space or in energy space. So let's see in real space how this works. So you can actually compute something that's called the local Chern marker, which is something that is simply the Fourier transform of the Berry curvature. You Fourier transform the Berry curvature to real space, and you'll get this formula, which depends on the commutator of Qx and Py. P is just a projector towards the ground state of your system, so you're projecting to the field states, and Q is 1 minus P. So a commutator over a finite Hilbert space is 0, so that's mathematically why this is 0. And if you plot it like a space result, you just choose some localized basis and plot this for your favorite Chern insulator, you'll get the following picture, where quantization happens really in the bulk. So you see that here I chose to fill a band with Chern number -1. So the bulk is really nicely quantized to -1. So when I average over the bulk area, I would get -1. But the edge states contribute exactly, if I sum over them, they contribute exactly with the opposite sign, and they exactly cancel the bulk. So this is why you get 0. So since the quantity I was talking about is exactly related to this local Chern marker, then you will get 0 if you average over the whole sample. If you just probe the bulk of your system, you get quantization. And you'll see why I insist on this later on. Now, if you want to see it in real space, you can actually, in energy space, you can actually calculate this absorption by looking at which transitions contribute to it. So you take the Fermi-Golden rule, and you calculate matrix elements, and you separate the ones that connect bulk to bulk states, edge to bulk, or edge to edge. And you'll see that the edge to edge, kind of as you increase your system size, exactly go to 1, the bulk exactly go to -1, and the edge to bulk kind of go to 0, and they die out. So the edge to edge and the bulk to bulk exactly cancel in the large system, large but finite. Okay, so this is kind of the energy resolved version of this property of this diagram. And now I want to use this to somehow filter out one of these contributions to distinguish chiral higher order topological states. And later on, we'll ask the question of how this topological content is actually distributed in real space. So here's my one slide on higher order topology. So so higher order topological states, you can define in many dimensions, but we're thinking about 3D and also time-reversal broken. So this has been studied by many people, including Andrea and others. But we used some models that this paper that I just put here because it's the model we're using. It's just a combination of two models that appear here. So what is this? What are these models? which kind of interpolate between different types of states. So you have a strong topological insulator if you want, and then you gap it out in two ways, either by a Zeeman coupling, so this just depending on where it points, it'll gap different surfaces. So it will break time-reversal symmetry but preserve inversion. And the term that preserves C4Z rotations combined with time reversal, but not these symmetries independently. So by modulating the parameters of this model, you can go from a TI to states that have to 3D states that have chiral hinge modes in different hinges depending on the parameters. So these are the two models that we have studied, and I'll kind of relate this one to something that has been proposed as a material candidate for this paper. So let's see what do we get. So here's this difference absorption rate plotted as a function of frequency. The particular shape doesn't really matter. It depends on the band structure and the peaks you get in different absorption, on the joint density of states and so on. But what I want to highlight is that it depends actually on the polarization plane that I choose. So let's say if I shine light, circularly polarized light in the what did I choose? XY plane, then I get some finite result, which is this curve, the solid curve. If you shine light in this XZ plane, so you turn this off and you shine light now in the XZ plane, you get exactly 0. So this means that there's some surface dependence on this absorption, and you can see it already. Let's say you take the one that does not give 0, which is this XY polarization, and you'll get something very similar to the Chern-Slater case I was saying. The bulk contribution gives a 1 in this case. The edge or hinge if you want gives something that's opposite and equal, and then the edge to bulk and bulk to edge actually, which I'm not showing, actually vanish. So of course the total sum is 0 because I showed you that for a finite sample, and this is a result that is independent of dimensionality. So for a finite sample, the total circular diagram is 0, but the bulk and the edge are contributing in a non-trivial way, one with +1 and the other one with -1. So how do you understand pictorically this? Is that well, what you're doing is basically you're shining light with a particular plane of polarization, and you're projecting your whole state to that plane. So what you have to ask is whether you have some sort of Hall effect or 2D Hall effect projected to that plane. So in this case, you see that the hinge states exactly project into a closed circuit, and then you go back in some sense to the Chern-Slater picture. However, in the other plane of polarization, you get exactly 0 because, well, whenever you absorb left, you absorb with right, because the plane of polarization, when you project your 3D state into that plane, you'll see that whenever you have a left mover, you have a right mover. So you get exactly 0. Now, this is all very good, but I still haven't told you how to separate the bulk and the edge, because if you shine your whole sample, you'll get 0. So how do you do this? So how do you get quantization? Now, in principle, you could try to measure the bulk and say, well, the bulk is independent. You know, if my sample is large enough, then the bulk would already be quantized. But the problem is that you have to integrate over all frequencies. And if you ask an experimentalist, integrating over all frequencies is hard because there are many. So then and sometimes you actually have finite samples. So you might want to actually want to measure what happens to the hinge states, right? So most of the times you have, right? So then how can you filter this out? Well, a neat trick actually is that, in a kind of very simple, I think, in experiment, is to integrate until some cutoff chosen in such a way that is less than the bulk gap. And the reason is that if the cutoff is less than the bulk gap, the only states that are activated is going to be, the only transitions that are going to be activated is edge to edge, while the bulk are going to be not allowed because they require too much energy, and the edge to bulk are anyway going to die out if you have large enough samples. So if you calculate this, so here's what I'm showing. I'm showing now this delta gamma, this difference in absorption, integrated up to a frequency omega max. So here's the frequency. You'll see that more or less you have one, or like you have a jump at the beginning, and then more or less a flat line until, of course, this is kind of affected by finite size effects, but in principle, for larger enough samples, you'll get a jump until 1, and then it will be more or less a plateau until you hit the energy of the gap, and then something non-universal will happen and eventually die out to 0 as you go to higher and higher frequencies. So this is how you would tell, 1, where is your bulk gap, and 2, or your bulk gap, and 2, where your edge states enter in this calculation. So if you just measure this differential absorption as a function of integrating frequency cutoff, so this W omega max, then you'll get the quantized result coming from the hinge state. What's J? J is the hopping. Yeah, it's just the natural energy scale of the models we're using. Thanks. So just to pictorically sum this up, if you take your light source and point it into project it into some plane of polarization, then project your 3D state into the plane of polarization you chose, then you might get, for this inversion Hottie, which has a inversion protected Hottie, or sometimes referred to also as axial insulator, I believe, you'll see that this hinge state projects into an exactly closed surface, which in this case rotates clockwise, so then you get chair number 1. But if you choose the other direction, you get something that is anti-clockwise and get -1. However, for the roto inversion Hottie, this C4Z inversion Hottie, this will actually give either 1 or 0, as I was telling you before. So if in one case you would get a projection which is exactly similar to chain insulator, well, in the other surface, another plane of polarization, you'll get something that does not close. So now, what about experiments, real materials? Do we have somewhere to look for these things? There was a recent nice paper by Shidai's group in this unpronounceable compound, at least to me, which is antiferromagnetic in one phase, and you have a bulk gap. So these are the surface states that are gapped because of this antiferromagnetic state, and you have the hinge states coming along here, which are chiral because it breaks Stammersel symmetry, and in principle is like the Stammersel breaking cousin of bismuth, if you want. So we were seeing this this morning, how you can have helical edge states in bismuth, but in this compound, these things are actually chiral. So if you would shine circularly polarized light into this surface, and in principle this can be grown, then you would exactly predict a quantized response due to the projection of this hinge states that I was telling you about. Now, this kind of motivated us to ask as well, what was how does really, circular dichroisms related to this local term marker, how does this actually play out in a 3D sample, and what can you learn about it? So, an expectation that people that know about TIs know is that whenever you gap a surface of a TI, you basically get a half E squared over H conductance due to the gapped Dirac states. So this was known long ago, and you can do a very simple calculation. Basically, you can do a layer resolved calculation of the Chern number. This was already done in this paper by Joe Moore and Vanderbilt and Andreessen. And basically what you do is that you calculate this local Chern marker as a function of the height, this Z, and you see that one edge state, depending on how you gap it, but one edge state contributes with +1/2 or -1/2 if you choose the opposite sign, and the other one does the same. So basically, at each surface you have a half quantized conductance in units of E squared over H. Now this is a universal property of topological insulators. But I just told you that in a Chern insulator, actually this bulk quantization gets exactly quantized, exactly compensated by the edge states. So how does this play out in a higher order topological insulator? So here's, if you choose a particular polarization, let's say a particular realization of this local Chern marker, I chose it to be in the XY plane, then you'll get a contribution, this red contribution coming from the hinge states, something that is basically 0 in the surfaces that are perpendicular to this x, y plane, and then something that looks close to -1/2 in the top and bottom surfaces. So let me zoom in, and you'll see exactly what you expect for the bulk. So something that is close to -1/2, and it's not exactly quantized because you have to make this larger and larger. But if you look close to like this central dots are the ones that are easier to converge, so you get very nice quantization here. But then you get some opposite sign contribution from the hinge states, which is maybe not so surprising given what I told you already. However, one thing you notice immediately is that, of course, if I sum over the whole surface, the local Chern marker for a Chern insulator is 0, but for this higher order topological state is not 0. It's, in this sense, you can already see that it's not coming from a 2D state, but rather a 2D surface. And moreover, this average, contrary to what maybe one could expect, is that unlike the bulk, which is always quantized to -1/2 or +1/2, the average over the surface is actually non-universal. So how do you see this? You kind of separate. You have to separate the bulk, or the surface bulk, with the contribution of the horizontal hinge and the vertical hinge. And now you try to make. If you have this very symmetric drawing here, you might think that the horizontal hinge and the vertical hinge actually contribute the same. And it turns out you can change the hopping in this vertical direction without spoiling the symmetry that protects this state. So basically, you can kind of elongate the cylinder or reduce it in the z direction. And now I'm seeing how the weight of the local Chern marker between the hinges changes. So let's look first at the bulk. The bulk is the average over the bulk, which is a bit of a thicker surface because the penetration depth of the surface states. The bulk is basically quantized to something that is close to 0.5. Again, it's quite a small system, so if you look at just one point here at the bulk, it would be very close to 0.5, but the whole average is a bit off. But that's in principle okay. Now the different symbols, you see that the different symbols basically fall on top of each other, and they represent the asymmetry between the hoppings in the vertical direction and the horizontal direction. But now if you look at the hinge modes, the hinges actually, if you get a very symmetric, totally symmetric hoppings in the vertical and the horizontal directions, then this contribution of the hinges goes to the same value. But as you start deviating from this very symmetric limit, which are these other crosses and dots, then they start deviating. And so this is telling you that if you sum over the whole surface, which is this extra line here, you actually can get whatever you want, essentially. So this is telling you that this local Chern marker of a single surface is actually non-universal. The bulk of the surface is universal, but if you add the hinges, it's actually not. So that distinguishes basically from a Chern insulator. This is my final slide. I'm just going to sum up. I told you that basically the quantized circular dichroism distinguishes different types of higher topological states, chiral higher topological states, basically by measuring the projection of the Hall conductivity to the plane of polarization, and the average of the local Chern marker, or how this local Chern marker is distributed over the 3D space, actually distinguishes the surface of a higher order topological insulator from a trivial Chern insulator, even though you might think that you can deform one into another just by thinking of a sphere, for example. But okay, so this is my final slide, and thank you for your attention.
You make a big sort of like torus where the inside and the outside are like. So if you make a hingeless torus out of the hobby, is the local Chern marker quantized then on the inside and the outside?
Hingeless. Okay, so let me understand. So hingeless.
So I make it periodic in two directions and just have a surface on the inside and the outside, basically. So it looks like a hollow donut, but like it's just like connecting the x and y directions there. Like there's a top and a bottom, and it's infinite this way.
Okay.
And periodic, let's say, yeah.
And what's the question?
Is the local churn marker quantized on the top and the bottom then if you get rid of if you kill the hinges?
Okay, like the bulk definitely is quantized. I think in that situation, yeah, I think the claim is that basically the symmetry doesn't impose that the horizontal and the vertical hinges contribute the same, but
Okay.
but the horizontals, all the horizontals contribute the same because they get mapped into themselves. So I would say in that case it would be quantized.
So you get a half and a half or half minus half on that?
Yeah.
Okay, cool.
So could you go back to the slide where you have the argument for why the total circular dichroism vanishes?
Okay, so I have several.
The one,
Let's say this one.
yeah, this one's fine. Okay. So you have this formula where you say that it vanishes because it's the integral of the local churn marker. The local churn marker integrates to 0. In the previous slide, you said that it was also the real part of the DC Hall conductivity.
Yeah.
Okay, but certainly for a finite size system, the real part of the DC Hall conductivity is non-zero. Because I can, connect my terminals and measure it. So it seems like there's something going on with the Q and omega limits.
Yeah, that could be. Yeah. I mean, it's different. I mean, as you know, like measuring transport and measuring optics is not the same thing, right?
So is the sigma Hall omega equals 0 that enters into this formula for delta gamma at Q equals 0 or at finite Q?
I would say it's taking the Q to 0 limit first. So it's at 0Q, but you've taken the Q to 0 limit first.
But if I take the Q to 0 limit first, then I get nu over 2 pi for a two-dimensional system.
But is this not just because there's no magnetic field? I mean, sigma xy should be 0.
No, but I mean, you've broken diversal. So, but I mean, if you're thinking of if you're measuring in contacts, let's say you're measuring the edges.
Well, I can do it with Laughlin flat pumping as well. And it's still. I know. I suspect there's something subtle with the Q goes to 0 limit.
Yeah, I would have to think about what is exactly going on.
Q goes to 0, it's R goes to infinity. So
Yeah.
it means you make a.
Yeah.
So if there's something subtle, so it will be there. Can't define a sample.
I mean, mathematically, it's just like local churn marker mathematically is very easy to prove that. It has to go to 0 because it's.
No, that part,
Yeah.
that's totally clear. The thing that's not
Then
clear
the-
is
yeah,
why,
yeah.
in a finite system, the integral of the local churn marker is the Hall conductivity.
I think it's probably something. Yeah, it's tricky to take the thermodynamic limit then, I guess. Okay, that's
So I'm actually also a little bit confused with that. The sum rule is equal to the DC Hall conductivity, right? Is that generally true? So for an experimental system, that you can actually have the DC Hall conductivity to have extrinsic contributions, right? Say the anomalous Hall conductivity that has skew scattering, side jump, and that type of stuff.
I think this argument is independent of what enters the Hall conductivity, because it's just a matter of how much power is absorbed, and then if you have impurity states, they can contribute.
Yeah. That's the thing that I'm actually a little bit confused, because the DC part of the anomalous Hall conductivity can depend on whether you put scattering in it or not. But when you sum up over all the frequencies, it seems to me that part, the sum rule part, is just related to how many, the density of spins in the system. Right, so there's a well-known optical sum rule that when you integrate over all frequency, that's only dependent on the number of the density of atoms in the system.
But that's longitudinal part.
Yeah. So if you take into account the off-diagonal part, that is it actually related to the number of spins or number of dipole moments?
I don't think the off-diagonal part is related. I mean, I think the off-diagonal part just measures whatever Hall conductivity you have, including.
So the integral would then depend on how dirty the system is, right? So it depends on whether Because the DC part of the Hall conductivity
Yeah.
depends on whether you have skew scattering or not. Then the corresponding integral will just dependent on that, not related.
Yeah, but it's the integral of the imaginary part of the sigma x y. So maybe I have to understand better your point, but I think as long, I mean, the proof is quite general. I mean, you don't assume anything about scattering. I guess one thing that assumes, okay, that maybe implicitly I assume is that you have translational invariance because you know, this area factor there like in general, this formula actually you have to integrate over space. So maybe that's where the subtlety comes from, and maybe that's actually a way to answer Federer's question.
About this chiral Hall-T, you argued it's true if you only you just mirror a kind of equivalent Hall conductivity. That is, you'll also get quantized.
Yeah, you could in principle add contacts and.
That's like it's a complicated quantum Hall.
Yeah, but I would argue that optical experiments are always cleaner, in the sense that, you know. So I'm
Then 10 to the minus 12 quantization of Hall conductivity.
I can tell you not.
Yeah, I mean, supposedly the spin Hall effect should be quantized as well. But yeah, in principle, I guess the problem there is that, you know, if you have a sample of, if you would have to attach contacts, I don't know, Philip can tell us, but it seems kind of tricky to attach contacts in different ways in different surfaces for the same sample. While here you just have to, you know, shine light with one plane of polarization and basically, you know, rotate your sample or something. It seems to be easier. I don't know. You can correct me.
I'm not so sure that you need that, because even if you contact the entire site, there's only one mode touching it, right? On the bottom. So I think this you could do. But actually, I have one other question. In all of the things that you considered in 2 and 3D, it was kind of from a topological point of view of your sample, somewhat of a contractible sample. So what if you add a hole or something non-trivial to the shape? Will this then basically form also a Hall-T inner?
Yeah. So actually, this might relate to what Raquel was telling us this morning. Like if you have some defect, and this defect carries a, let's say, take this location that has a quantum spin Hall. Now take the chiral version of that has a yeah. So that would contribute to the circular dichroism for sure. So then, in principle, it would be you could detect defects that have edge states around them as well.
But if you just would drill a mundane hole, not this type of chiral defect, just make a hole inside. Because it seems to me that then
you have to drill it respecting the symmetry, though. Like if you break C4I, then everything is fine.
Yeah, sure.
Okay, then that would contribute as well. Like anything that projects to the plane of polarization that has a non-zero, or like let's say a closed circuit will contribute. So you would have to, let's say, take that contribution times the area of that hole and subtract it with the contribution of the outer edge and the area. So basically, it would be a difference of areas. You have to. There would be some geometrical factor in it that you would have to take into account.
But would you not be able to then probe? I mean, wouldn't that be a very nice probe? Because presumably the outer state wouldn't change. It doesn't care if you drill a hole in the inside. But you now change the flux. Right, so the flux to the outer thing will still be the same. But then now you capture some flux in the inner thing, which if it's an entirely local state of some sort, you shouldn't care.
I'm not sure I know what you mean with capturing flux, but
well, or light, the area projection that you used.
Yeah, that's right. Like if you drill a hole, it will contribute as well to this, or at least it would, say, subtract part of what you were seeing without the hole. So yeah, that's addition.
Okay.